We can also look at joint probability with these contingency tables. So again, joint probability refers to the probability of the occurrence of two or more events. So what's the probability that you pick a random day in 2015 and it is not January and it is not Wednesday? Well, the probability that it is not January and it is not a Wednesday is right here, 286. Again, we divide it by our total sample space. So the probability it is not January and not Wednesday is 286 out of 365. What's the probability that we pick a random day and it is a Wednesday and it's in January? Well, here we have Wednesday, January, and it's 4 out of 365. So this may seem very familiar because we did calculate percentages in Chapter 2, but this time we're just wording it in the terms of probability. Mutually exclusive events are events that cannot occur simultaneously. So for example, a day in January and a day in February, those are mutually exclusive because those cannot happen at the same time. Same with a deck of cards. The probability that it is a red card, the probability that it is a black card. Those are mutually exclusive events. Collectively exhaustive events means that one of the events must occur and the set of events covers the entire sample space. So for example, if we take these right here, weekday, A is weekday, B is weekend, C is January, and D is spring. A, B, C, and D are collectively exhaustive, but not mutually exclusive. A weekday can be in January or in spring, but the set of those events does cover the entire sample space. Events A and B are collectively exhaustive and also mutually exclusive. So being a weekday and a weekend, that covers all of the sample space of the year of 2015. And if it is a weekday, it cannot be a weekend, so that those are also mutually exclusive. So the equations here can be kind of confusing. So rather than memorize these equations, you can also use the contingency table that we looked at earlier. But here, the probability of a joint event of A and B, we usually look at how it's written out as the probability of A and B is equal to the total number of outcomes satisfying A and B over the total number of elementary outcomes. And then here's how you compute a marginal or simple probability. Well, we could use those, or we could just look at a contingency table here. So the probability, again, of a January and Wednesday, here we have probability of January and Wednesday out of 365. And then to compute marginal probabilities, again, that is just that total column here. So the probability that it is a Wednesday, we want the probability that it is a January Wednesday, as well as the probability that it is a non-January Wednesday, and that'll give us 52 out of the total sample space of 365. So instead of using those equations, which you can use if you prefer, I prefer to use a contingency table, but here we have in the middle of the contingency table are the joint probabilities, and then our total columns here are our simple probabilities. And the probability summary so far, so the probability is a numerical measure of the likelihood that an event will occur. And the probability of an event must be between 0 and 1, such that 0 means that it is an impossible event, it'll never happen, and then a probability of 1 means that event is certain and it for sure will happen. The sum of all probabilities of all mutually exclusive and collectively exhaustive events is 1. So if you take the probability of A plus the probability of B and the probability of C, if those are mutually exclusive and collectively exhaustive, then that probability will be equal to 1. So here's another example. If I collected data on students and they either attended class regularly or they did not attend class, and then I looked at their scores, if they did well on the exam or they did poorly on the exam. So the variables of attended class regularly and did not attend class are both mutually exclusive because you cannot be both of these at the same time. You either attended class regularly or you did not attend class. And they're both collectively exhaustive because if I add up, these totals here for both students who attended class regularly and did not attend class regularly, that makes up my entire sample space. So the next couple of slides will contain some complicated probability equations, and probability can definitely get very confusing and convoluted and complicated. So for practical terms, I won't make you calculate these probabilities or follow a specific formula, but I would like you to be aware of the general ideas. So you can calculate the probability of an event or another event. So for example, if you want to calculate the probability of a random day being a January day or a Wednesday day, you can use this formula where it's the probability of A or B is equal to the probability of A plus the probability of B, and then you subtract the probability of A and B. So here's an example here. If I want to know the probability that that day is January or a Wednesday, we take the probability of a January day, which is 31, the probability of a Wednesday, which is 52, and then you subtract the probability of it being a January and a Wednesday, basically because we don't want to count them twice. And then we get 79 out of 365. Again, I won't force you to do these calculations because they can easily be done on the computer, but I do want you to be aware that you can calculate probabilities for two separate events in an OR situation. We can also look at conditional probabilities, and conditional probabilities is the probability of one event given that another event has occurred. So here are the equations here. This line right here just denotes, given that. So the probability of A given B is the probability of A and B divided by the probability of B. Or if you want to go the other way around, the probability of B given the probability of A, the probability of B given A is equal to the probability of A and B over the probability of A. So here's an example of the cars on a used car lot. 70% have air conditioning and 40% have a GPS. 20% cars have both. What is the probability that a car has a GPS given that it has AC? So you kind of have a parameter that you kind of have to fill first, which is that AC. So again, we can use that complicated equation, the probability of having a GPS given that it has AC. We have the probability of a GPS and the AC, which is 0.2 here. We can find that from our contingency table, divided by the probability of having an AC, which is 0.7. So the probability of having a GPS given that you have an AC is 0.2857. Again, I won't force you to calculate these things, but I do want you to know that you can calculate conditional probabilities. Another term that you should know is independence. So two events can be independent if the probability of one doesn't affect the other. So for example, the probability that you are a WT student and the probability that you like sandwiches, those are completely independent. Just because you like sandwiches does not, increase your chances that you're a WT student, or just because you're a WT student, increase your chances of liking sandwiches. We can also find the probability that two events occur together. Now, what I would like you to know is that if A and B are completely independent, then the probability of those two events occurring, all you have to do is multiply those two probabilities together. So here's an example. Let's say I polled my class and I find that the probability that my student is a swimmer, a random student is a swimmer, is 0.13. And I also ask where my students are from, so the probability that my student is from Texas is 0.74. Now I want to know, what's the probability that the student is a swimmer from Texas? Being a swimmer and being from Texas are completely independent. One does not depend on the other, or being one does not increase your chance or decrease your chance of being the other. So because these two are independent, to find the probability that both of these events are occurring, all I have to do is multiply them together. So that's 0.23, which is the probability of being a swimmer, multiplied by the probability of being from Texas, is equal to 0.1702. So the probability that a student is a swimmer from Texas is 0.17.